What is going on, everyone? Happy Thursday, or whenever you were watching this. This is just to cover the last couple of slides in greater detail, since we are canceling class on Friday. So, starting off, we have advanced file operations. This is more or less just an extension of these iOS : flags that we can set. So, like I mentioned in class, we can utilize the fstream operator instead of ifstream and ofstream. If you want a bit more detail on that, it's like inheritance, and like fstream is the parent of ofstream and ifstream, so it works with both. It's funky. So, what you need to know for it is with these different flags, you can combo them. And so you can have an input and an output file. You can have an output file that also appends and stuff like that. So looking at the different flags that we have, realistically, you're only going to use 2 or 3 of these. So the first one is iOS : app, and what it's going to do is append to the file. The kind of rules that it has in the background is that any output that you give the file is going to be written at the end. Looking at the next flag, we have iOS : 8. No thank you, I'm full. Hopefully I got a chuckle, at least one of them. So if the file already exists, the program is going to go to the end, but you can go back and change things in other places in the file. So the difference between the two is that they both start at the end, but 8, ATE, is going to allow you to write to other places in the file. We have an example of that here in a bit. The next one is iOS binary. In class, I was hating on this because I'm like, who needs to read and write in binary? But it is actually more efficient in a lot of scenarios. So the idea of it is that we speak to the computer in computer language, zeros and ones, maybe hexadecimal. So it's not human readable, but it is computer readable. And it ends up being faster, but we'll talk more on that in a few slides. The most useful one for fstream, in my opinion, is iOS : in. This just specifies that it is a input file, and it allows us to treat it like ifstream. And then finally, one that we all should know by now is iOS trunc, which is just truncate mode, or as I called it, overwrite mode. Whenever it opens a file, it's going to overwrite anything that is there and add new input in. So another couple of functions that you can use with these files is get and put. The idea of it is it reads a single character. I've never really used it, but if you do need to read a single character and you don't just want to use insertion stream operators, this will work. So I'm going to skip this because hopefully we can trust that these work with characters. And now on to the bread and butter, the part that I'm surprisingly excited about, binary files. So I've talked about binary a little bit in class, but the idea is that it is just straight, pure computer language. It is zeros and ones throughout. A couple advantages of it is that it is more space efficient and time efficient. Whenever you work directly with zeros and ones, you don't have to translate between human readable text and computer readable text. It is a genuine benefit. And the way that we specify that we are opening a file, whether input or output, as binary is with the iOS : flag down here at the bottom. So whenever we work with these binary files, we can't use the stream insertion and stream extraction, or alligators as I call them. We have to use a specific function called read and write. So this is, it's like old C. You know, C++ is like the I want to say Gen Z, it's the millennial language. Pure C is like boomers. So with this, we have to explain basically exactly what we want from it. So in this case, if we look at the example on the screen where we are doing infile.read, we do some funky stuff. So we are passing character by reference. Haven't officially covered that yet. I've mentioned it maybe. But the idea is we are saying, hey, I want you to read directly from this memory address. That's what we're specifying. We're not working with the values, we're working with the memory address. And then we have to tell it exactly how much to read. C is disgustingly manual, but it is a beautiful language when you understand it. So what this line says is, hey, go to this memory address and read a single byte. I lied. Go to the file, grab me a single byte, and place it within character. That's my bad. Down below we have outfile.write. This is what I meant to say. In which we say, go to where character is stored in memory, grab me a single byte, and place it in our out file. Now, this is when it starts to get gross to understand. So if we want to read and write non-character data, we have to typecast. Now, typecast is a concept that we've talked about, right? It is static cast. It's how we go from one type to another, whether it be ints to doubles, strings to doubles, things like that. We get messy here. For the whole maybe one person that's sitting at their computer and asking, oh, but what's reinterpret cast? I could explain it, but two things. One, it gets into compiler talk, and that is deep, dirty, is hands-on, and two, I can't tell you the definition. I took 5 minutes, Googled it a bit. It's like static cast, but it meets the criteria of the compiler more. So, if we want to work with non-character data types, we have to trick our compiler, basically. And so, if we want to read in a it's a char star, you can read this as like a C-style string, an old string, basically. My bad. So if we want to read a non-character or a non-string from a binary file, we have to say, hey, grab me it, and then cast it from a char star to our number. Disgusting, I know. But we pass it the size of an integer. I believe that is 4 bytes. But we tell the file, hey, go grab me 4 bytes and put it in num. If we want to output a non-character value to the file, we do the exact same thing. We tell it, hey, write this number as a char star and do 4 bytes. You do not need to know the nitty-gritty of this. This is gross. So, I'm not actually going to use this example. I will upload a different example. I went and petitioned our AI overlords to help me write this. And we have 2 examples to show off. So with this first one, binary.cpp, we are just outputting a couple things to a file and then reading it back in. So if we look, we have a character array, which is an old string that holds name warrior, a warrior named Warrior, sure, who is level 10 and has 100 health. To write to the binary file, we open it first as binary. So we're opening character.dat, so data, in iOS binary, and then we write to it. So for characters, we don't need to static cast. For the integer and the float, we do have to static cast. After that, we read it back in, and then we print it to the screen. So nothing too scary going on. So let's give this a run. So binary.cpp. So we read from the file, or we output to the file, we read back in from the file, and we print to the screen. I am going to do a little bit of Linux trickery to show you off what's going on. We do a hex dump on character.dat, and as you can see, this file, whenever we tell it to show us the actual hexadecimal that's going on, that stuff. those are in fact numbers. If we sit here and do a little bit of math, was that 42 in hexadecimal? That's probably 100. Because 64, 68, trust me. So, as you see, if we try to open this within our actual terminal or our VS Code, character.dat, that's readable. It's saying null, 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 null. Yeah, I understand what's going on there. So, I also have a file for large binary generator, and this just shows off, hey, what are the differences in this? And so we have truck going by, my bad. And we're good. We have 1 million numbers to work with. We are going to open 2 different files, one as binary, one as just a normal text file. We print out to both files, and then we close them. So this is just setting us up. After we do that, we are going to time how long it takes for C++ to read them using the chrono library. But we just read the numbers, stop the timer, and then do a little bit of math to figure out how long that took. Next, we are going to open the human readable file and do the exact same thing. So we read all of these numbers in, stop the timer, and see how long it took. So let me clear my screen, do large binary generator, and run it. So the good thing about C++ is that it is fast. This is the one main benefit it has to stuff like Python or any of these newer smart languages, higher level languages, is it is super fast. So for the binary file, it took less than a 20th of a second to read 1 million numbers. Whereas with the text file, it took about a 10th of a second to read. So just to prove this works, I will show you data.txt, and that is, wait, hold on. Okay, it's 1 million, had to make sure. But we have 1 million numbers, that is a couple of numbers. And if I open data.bin, that looks like 1 million numbers. So, one other thing that I want to show off, crack open properties of character.bin, and then that is data.bin and data.text. So data.bin is taking about 4 megabytes of space for 1 million numbers. Whereas if we store it in human readable, it takes almost 7 megabytes. Now, why would this be useful? Why do we care about this? Believe it or not, binary files are used a lot in the game industry to hold save data. It takes up less space on a computer, it's faster to read and write, so you have less load times or save times, and it's just generally better. It also helps you kind of hide what you're working on. That's more of like a 1310 or an OOP topic, but either way, it's pretty cool. And then for kicks and giggles, I will show you the hex dump of that. Yep, that's data. I understand what's going on. So for the last couple of slides, we're talking about random access files. So normally whenever we are working with files, we're doing it with sequential access. So we start at the beginning, we walk line by line, and we just work 1 to 100. With random access, it allows us to go anywhere in the file. The one caveat, whatever, being we have to work with bytes. So 2 different functions to do this. We have seekg and seekp, which stands for seek get and seek put. The difference between the two is one works with input files and the other one works with output files. So this slide just shows us we open the file, whether it be the input or output, and what we can really do with it. So with seekg and seekp, we have three different sort of flags that we can use. We have iOS beg for beginning, we have iOS cur for the current position, and then we have iOS end, which will work from the end of the file. And then the two examples we have on the slides, we can specify, hey, from the beginning, walk 25 bytes. If you remember, one character is 1 byte, so go 25 characters within the file and read something from there. The second one, we are starting from the current position, and we are backing up 10 characters. Now, the one thing I always talk about is that, where am I? I am lost. Data.txt, there we go. Is that the hardest part about working with files is figuring out where your cursor is. Whenever we do it with VS Code, we can see my cursor is on line 2. Whenever we're working with files, we don't have that visual indication. So, one other thing to note on this is that if end of file, if we've hit the end of file at any point, we have to clear it before we go back. This is just quirkiness, I guess. One other thing that we can use is tellg and tellp, which just tells us where we are currently at in the file. So if I open this file and I say, hey, tell me where I'm at, it's going to say, oh, you are at the 8th byte, because I'm on line 8, and each line is 1 byte. And I will crack open random access file to sort of show this off. So if we come over here, we are working with letters.txt, and I'll show it off. It is one line of the alphabet. A, B, C, D, E, F, G. I hope you know your alphabet because I'm not saying the rest of it. And this just shows off working with iOS beginning, iOS current, and moving it around. So at the very beginning, we are telling it to take 5 steps and get the byte that is 5 steps in. Next, we are going to back it up 10 from the end, and then 3 more down from the current. So let's give this the good old college try at running. So 5th byte from the beginning is an F, so if we come over here and we go 1, 2, 3, 4, 5, puts our cursor right before F. 10th byte from the end, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The very next byte is going to be a Q, and if we take 3 more steps, 4 more steps, I guess, we get U. So, because we would read Q and the cursor would go. That makes sense. So, the downsides with this is since we have to work with bytes and we can't just specify lines, we have to get a bit more down and dirty with it. One benefit is that if every single one of your lines is the exact same length, this is great because you can say, hey, skip 500 steps down and we'll end on whatever line. And that's one big benefit of it. But seekg and tellp are 2 options you can use. And that is it. What am I at? 18 minutes. Do I need to put Subway Surfers down here? Hold on. I got this. I got this. Actually, I'm not showing my YouTube. Y'all made fun of me for it. So, hope this made sense. If y'all have any questions, let me know. And I hope you have a fantastic Friday or whenever you watch this.